Greetings, physics fans. We're going to talk about the average kinetic energy of particles in a gas. So if you watched my Boltzmann's constant video, you would have seen that we said that the internal energy of a gas you can write as, well, we normally would write as 3/2 nRT for a monatomic gas, which can become 3/2 n, which is the number of particles in the gas, over Avogadro's number, times the universal gas constant, which is going to be Avogadro's number, times Boltzmann's constant, times the temperature in Kelvin. So we can cancel those two Avogadro's terms out, and then have a different way of writing this equation. So I can say the internal energy of a gas, for a monatomic gas, for a diatomic it would be 5/2. Number of particles in the gas times Boltzmann's constant times the temperature. So now if I want the energy of each particle, the average energy of each particle, right? That's going to equal U over N, right? So energy per particle, which is going to be 3/2 Boltzmann's constant times temperature. So, and what kind of energies will a monatomic gas particle have? I love this. I'm so excited. What kind of energies will it have? Because we're in an ideal gas. Because in an ideal gas, we said there are no forces between the particles, right? No intermolecular forces. And we're going to say they're light enough that we don't have to worry about gravity. So what types of energy do they have? So, well, they don't have potential energy, if these assumptions are true. That means they only have kinetic energy. And if they only have kinetic energy, I'm so excited. I can now say 1/2 mv squared is equal to 3/2 Boltzmann's constant times temperature. Oh, so good. I'm so excited. So I can then cancel my 2's, right? Gone. And I can now solve for the average speed, or RMS speed, of a particle in my gas. Oh, so good. I'm loving it. All right. So I want the speed by itself. So I'm going to divide by m. Then I'm going to square root both sides. So I'm going to get v squared equals 3kbt over m. And then v is equal to square root 3kbt over m. Let's make sure this looks like it's in there, in that square root. Oh, so good. So good. So that is the RMS speed, the root mean square speed of an atom in a gas. I hope you guys are half as excited about this as I am. So let's write VRMS and put that in a box. Oh, so good. So good. So what can we do now that we know that? Well, knowing that, I can probably do something like calculate the collision with walls and how much force they deliver, right? So do you remember before when we did a problem of a ball bouncing off a wall, right? And you said you've got a ball coming towards a wall. And it's going to bounce off like that, right? And it's going to angle theta. It's a momentum problem. This is also going to be angle theta because of the law of reflection. Well, we said that in the x direction, right, the momentum changes because you have momentum this way. So you have px, you've got py, and here you've still got the same py, because that hasn't changed. They're still in the same direction. But here you have minus px. It's in the other direction. That's an x. So what your change momentum, your delta p, is going to be minus 2 px, right? Or we could write this as minus 2 mv cosine of theta. But now we know what that v term is when it collides, or at least on average. And since we're talking about 10 to the 23 particles, the average is pretty good. So now, if I want to figure out the force each particle delivers, now I need to know how long that collision lasts, right? Because I could say force equals delta p over delta t. So I can figure that. If I can figure that out, then now I can figure out that force. Or maybe I already know the force, the total force from the pressure, and if I can divide, right, this is momentum to be clear. And this is momentum also. But I also know that pressure, that's pressure. Need to differentiate equals force per area. Right? Hi, Cicero. Alright, so I think the truck's gone that he was barking at. So if you know the total force on the wall from the pressure, and you know the number of can figure out the number of collisions happening per second, you can figure out the duration also. So there's a couple ways to look at this, but I'm going to go ahead and end it here, because I think we've learned something here about the speed of a particle, and we've also maybe remember something about momentum. All right, see you in the next one, guys.